Good day, students. How are you doing today? You're welcome back to the class. So today we are going to look at further mathematics, and the topic we are going to treat is vectors. Vectors one. So meaning that the vectors will be in two different parts. So but this one we are going to first of all take the vector one. And taking the vector one, these are going to be the specific objectives we are going to learn at the end of the class. So let's start with that. Now, before we start with that, we're going to first of all take the first objective, which is talking about what scalars and vectors are. From our previous knowledge about physical quantities, we know that physical quantities are divided into two, which are the scalar quantities and the vector quantities. The scalar quantities and the vector quantities. And what do we say that the scalar quantities are? We say that the scalar quantities are those physical quantities that are specified with only what? Magnitude. So they can only be specified by their size or numerical value. So we say that vector quantities are those physical quantities that have both magnitude and direction. So meaning that they can be specified in both magnitude and direction. They can be specified in both magnitude and what? Direction. Now, recalling back the examples of scalars which we have treated in our previous classes. Examples of scalar quantities or quantities that can be regarded as scalars include 1. Length or distance. We can also talk about other examples include time, temperature, talk about I've talked about time, I've talked about then mass, we talk about energy, work, and etc. Then talking about some few examples of quantities which are regarded as vectors, they include physical quantities like displacement, velocity, we'll talk about acceleration, we'll talk about force, we'll talk about momentum, we'll talk about electric current, we'll talk about and field forces, etc. So we have plenty of them which we are going to get to. Now, let's go into the next thing we have. Now, talking about the simple operations of vectors, there are a few different terms which are important that we have to know about vectors. Now, remember, we just differentiated between scalars and vectors. We are not interested in vector quantities, scalar quantities. We are just interested in what? Vector quantities. So we just differentiated between them. So, but in the period of this class, we're going to be treating everything that concerns what? Vectors. But before we go into these simple operations, I want to tell you that just like we defined vector, that vector are those physical quantities that have both magnitude and direction. So it will help us to know how vectors are represented. How do we represent vectors? We represent vectors using a straight line with an arrowhead. A straight line with an what? Arrowhead. So simply, we have a straight line with an arrowhead. Now, the straight line, the magnitude of the length of the straight line is telling us or signifying or representing the magnitude, which is the size of the what? The vector. While the arrowhead is showing us the direction of the vector. So, this straight line, which is the length of the straight line, is representing or denoting the magnitude of the vector, while the arrowhead is denoting or representing the direction of the what? The vector itself. Now let's take for an example. If we consider a point, let's say B, from another point A, which is 50 kilometers, in the direction of north 45 degrees east. This simple statement I made now can be represented with a vector diagram. I said a point B from another point A 50 kilometers in the direction north 45 degrees east. If I want to represent such vector statement as a vector diagram, all I need is for me to measure north 45-degree east. So this, remember that every point has four cardinal directions. So, and this is my north, and this is my what? East. Now, it means the northeast direction is a direction that is between the north and the eastward direction. So that is, I will measure 45 from north going towards the east. So this is what I'm going to have. With using my protractor. Then after which I will use my straight line to measure 50 kilometers. But you know that you cannot use 50 kilometers in an exercise. So what you do is to use a scale. You can decide to say, let 10 cm represent 10 kilometers. So meaning that the 50 kilometers will be now be scaled to 5 or cm. So this is 50 kilometers. So but here is point A because the point is from A, while here is point what? B. So this is the vector representation of the that particular statement. All right. So the next thing we are going to look at, let's look at the simple operations on the vectors. Now, for us to look at simple operations here, there are a few terms that are important we need to explain. What are the few terms? One is what we call magnitude of a vector. Magnitude of the vector. Now, what do we mean by magnitude? Magnitude, which can also be called the modulus of the vector, can be obtained as just like the statement modulus. It's just the normal modulus we know. In the sense that if we have a vector, for example, let's say a vector r, which is given as, let's say, a in this direction, okay, let's say x in direction I plus y in direction j, these are called the unit vectors, then the modulus of this can be written as this, just like is we know absolute value of r is the same as the modulus. So when we find this, we have it as square root of x squared plus y squared. We will talk about this more when we go to magnitude of vector, but I just want us to talk about those terms that we'll be seeing along the course. Now, another thing we are going to look at is what we call negative vector. What do we mean by negative vector? Negative vector is a vector that has the same magnitude but moves in opposite direction with a given vector. Let's take for an example. We have a vector, let's say, which is represented like this. Let me say this is vector A. So vector A, the negative vector A will be a vector that will be drawn in the same parallel direction but in opposite what? Direction. So this is A, while this is negative vector A. So that is it. So having done this, the next thing we will talk about is what we call equality of vector. When we say that two vectors are equal, it means that those two vectors must have the same magnitude and they will also move in the same direction. Alright. Then the final thing we will look at is what we call unit vector. Unit vector. What do you mean by unit vector? A unit vector in a given direction of a vector, let's say A, let's say that vector is A, in the direction of A, is written as A cap, that is having a cap on top of A, such that this vector A can be obtained as the product of the modulus or magnitude of that vector and the unit vector. So meaning that unit vector A is equal to what? A upon magnitude of what? A. So this is the expression for what? The unit vector A in the direction of vector A. So we will look at this when we are going to treat, we will look at how we can see the examples, how we can use a vector to solve that problem when we get to this last objective here. So having done this, we will now go into the sum, difference, and scalar multiplication of what? Vectors. Now, before we talk about this, there is what we call resultant vector. What is resultant vector? Resultant vector simply means that single vector that has the same effects when two or more vectors act what? Together in magnitude and direction. So when two vectors are added or subtracted from each other, the result we obtain is called a resultant vector. When two vectors are acted together, whether through subtraction or addition, the result is what we call the resultant what? Vector. Now, in addition of vectors, there are two basic methods which we apply in addition of vector, and those two methods are what we call the parallelogram law of vectors and triangle law of what? Vectors. Vector addition. Vector addition and subtraction. So this is the same thing as saying sum and difference. Okay, I said addition or subtraction of two vectors gives a resultant vector. And in doing this, we have two ways of doing that. And those two ways are the what? The triangle law of vector and the parallelogram law of what? Vector. Now, talking about the triangle law of vector. Assuming we have two different vectors, we say that the resultant of that vector can be taken to be the third side of that particular triangle. That is the triangle law of vector. I'm going to use a diagram to illustrate this because we know that vectors are always represented using what? Vector diagrams. So now, assuming I have a vector A, let's say vector A in this direction, and I want to add it to another vector, let's say a vector B in this direction. So let me call the starting point of A to be A, capital A, or let me just call it X, and call the ending point to be Y, and call the ending point of this place to be Z. So the resultant vector will simply be the same thing as moving from A to, X to what? Z. So this is the resultant vector. So in the sense I can call this distance from X to Z to be the letter C, showing the resultant vector. So meaning that A plus B is equal to C, because for me to travel from X to Y, which is A, and from Y to Z, which is B, is the same thing as traveling from X to what? Z. That's the shortest distance. So that is the resultant of these two vectors here. So if I should apply the triangle method, what it simply means is that x, y, please, this is another way we can represent vector using the starting point and the ending point of that vector with a small straight line and arrowhead showing the direction of that vector. So this is xy plus yz, that's vector yz, is equal to what? X what? Z. That is true. Xy plus yz is equal to what? Xz. Now we are still going to look at what we call addition of several vectors. We are going to, when we are done with this, I'm going to use it to show something very important. So xy plus yz is equal to xz. Now having done this, that relationship that holds for this is what we call the triangle law of what? Vectors. Triangle law of vectors. So what it simply means is that A plus B is equal to what? C. Now, these vectors A, B are the component vectors. YC is just the resultant vector. So let's take note of that. So that is addition of vectors. Now, talking about difference or subtraction of vectors. Okay, before I go into that, let's talk about the parallelogram law before I go into the difference. Now, talking about the parallelogram law, the parallelogram law of vectors is that the resultant of two vectors is represented by the diagonal of that vector, such that the adjacent sides of that particular parallelogram or the vectors are represented by the adjacent side of that parallelogram. I will take it again. I said the resultant of two vectors is taken to be the diagonal of that vector. That's diagonal of a parallelogram. If these two vectors are represented by adjacent sides of that parallelogram. So let's take for an example now. We have two vectors. Let's say P, Q, and P, let's say R. These are two vectors I want to add together. I can represent them as adjacent sides. Look at these two sides are adjacent to each other. So completing this diagram, I'm going to have this and this. So let me call this point S. So we are told here that the diagonal is taken to be the resultant vector. So assuming here PQ is A and PR is B, then let's call here C. So we are told that from parallelogram law that PQ plus PR is equal to what? PS. That's what the parallelogram law is telling us. So how can we write that? We can write that PS, which is the resultant, is obtained as the sum PQ plus what? PR. Now, looking at this we have here on the board, we already know that PQ is the same thing as what? RS. Is it not so? So what it means is that the vector PS is equal to PQ plus RS. Is it not so? So, but then, no, we say PQ is equal to RS. No, so we say that this is RS, because this is RS, plus PR, because we say that PQ is equal to RS. So PS is equal to, I can place this one first because I'm considering order. So this is PR plus RS. So if I add these two vectors together, because these two are together here, so I'm going to have this as PS. So telling us that PS is equal to PS. That is that PS can as well be obtained from what? PR plus what? RS. So in that case, what it means is that PS, which is C, is equal to or can be obtained from what? Our PQ is the same thing as our, okay, this is PR, which is B now, plus RS, because this side is parallel to this side, so here is also A, so that is it. Therefore, that C is equal to A plus what? B. So this is telling us that the diagonal of the parallelogram is the resultant of two vectors when those two vectors are represented as adjacent sides of that same parallelogram, which is taken to be the parallelogram law of what? Vectors. Now, for proper understanding and mathematical solving of mathematical problems under vectors, it is important that we should solve sum, difference, and scalar multiplication of vectors in component wise. So when I mean component wise, it simply means that vectors can have their components, just like what we know. Now, talking about the components of vectors, it is been a custom that vectors will always be resolved into two perpendicular components or directions. But the vectors that should be resolved to these two different or two perpendicular components are just vectors that can be represented on a plane. Now I'm going to use diagrams because vectors will be appreciated using diagrams. So with that, I'm going to capture this component of vectors or vector. Now, a given vector can have two different components. If this vector is represented in a plane, rather on a plane, what do we mean by vectors on a plane? Vectors on a plane simply means vectors that can be represented as two-dimensional vectors. Now, a vector can also be represented in space. So those kind of vectors are called three-dimensional vectors. So there, we say that those vectors can be represented using three components. So, but in this case now, we are going to talk about the components of vector in a plane below. So, component of vectors in a plane, because that's what we are expected to talk about at this level. Now, talking about components of vector in a plane, I said that it's been a custom that vectors should be resolved into two perpendicular components. Now, which components are we going to talk about here? That's the horizontal and the vertical components. Now, assuming you have a vector, now you have to listen attentively. You have a vector, let's say OR. This is a resultant vector OR. Now, it is possible that this vector can be resolved into components. And the component, because it's in a plane, it will be resolved into the vertical and what? The horizontal directions. Now, when I talk about the vertical directions, I'm going to use OX to represent OY to represent the vertical direction and OX to represent the what? The horizontal directions, which are the two components on which we are going to have these vectors. Now, assuming we use the letters I and J to represent the directions of these vectors that we're going to have in the X and the Y axis. So we're going to use I as the direction, which is, remember what I told you about I, that I is the unit vector, but we are going to use I to represent unit vector on the horizontal, and J to represent what? The unit vector on the what? On the vertical. Now, if we resolve this particular vector into their components, it means that the magnitude in x-axis and y-axis will be, let's take for example, we'll call this place the distance from here to here, because that will be the horizontal component to be small letter x. Maybe we should call here n, and call the distance from here to be small letter y. Maybe we should call here p, as the case may be. Now, from what we have learned about vector, it is important that we should write the position vectors of these vectors and see how we can obtain or write the position vectors in terms of the resultant vector. Now, I want to say something about the position vectors. When you have 2 points, let's say A and B, in the sense that A is the reference point of B, then there is what we call position vector. If we have a line joining A to B, in the sense that A is the reference point of B, then we say that the vector from A to B is the position vector of B with respect to B, or relative to A. I will take it again. I said, assuming we have 2 points, let's say A and B on a plane, and A is the reference point of B. That is, we want to measure B from A. So it means that the reference point is A. So if we have a line joining A to B, then the vector of B with respect to A is called the position vector of B relative to A, or with respect to A. So, but in most cases, we use a reference point to be O, just like when we have our two vertical axes, two mutual perpendicular axes like this on our graph. The point here is the origin here. So we always take this point as the origin or the reference point. So assuming I have a vector here, let's say vector A, the line that is joining O to A is the vector OA. And this vector OA is called the position vector of A relative to what? O. So here I can write the resultant vector. Let me use R as the resultant vector. But I can write this resultant vector in terms of the position vectors. So the resultant vector OR is equal to OP, or let me say ON plus what? OP. OP. That's it. So, but then I know that my OR is this, that is small letter r, is equal to, now look at this, x is the magnitude of this particular, I would say, component of this particular modulus or magnitude of the resultant vector along x-axis. So I will write r is equal to x, which is the magnitude on the horizontal. Because it's horizontal direction, we place it with its unit what? Vector. So telling us that x is in horizontal direction. And we remember that we use I to represent the what? The vectors, the unit vectors in the horizontal direction. Then plus OP here, the magnitude of OP is y. But what is the direction of y? J direction. So we have this. So R equal to xi plus yj is the component of this resultant for vector in x and y direction, or in horizontal and vertical direction. Remember, we said that it is a custom that any vector that is on a plane can be resolved into two components, which is the horizontal and what? The vertical component. So this is the magnitude on the horizontal, and this is its unit vector in the direction of what? X. And y is the magnitude on the vertical. Yj is its unit vector in the direction of what? Y. So r is equal to xi plus what? Yj. So whenever a vector is written this way, we say that that vector is written in its what? Components. Now, this, remember, this is only for vectors that are in a plane or two-dimensional vectors. That is, vectors that are represented on a plane, just like a board like this. Apart from writing vectors in their components, vectors can also be written as a column vector. What do we mean? It means that R here, which is our OR, can also be written as x upon y. So this is called the column vector. This is another way vector can be written apart from its components wise. This is the component wise. So this is the column vector. So assuming we have a vector, let's say C equal to AI plus BJ, that means, it simply means that C, to write it as a column vector, right, C is equal to what? A over or upon B. So assuming I have this vector now as R, let's take for an example, I say R is equal to 2I plus 3J, then this is the component wise. Then I can now write R as what? 2 upon 3. Now, having known the component wise and column vector, then we are going to look at the magnitude and direction cosine of a given vector. I want us to take all this before we now go into solving practical problems. Alright. Now, how do we express the modulus or magnitude? In terms of magnitude or modulus of a vector That is vector in a plane, that is two-dimensional vector. In a plane, in terms of its components, is important. In terms of its components. So, recalling back to the diagram I have on the board, let me still sketch up the diagram. I have my O and P, direction of Y, which is J direction, direction of X, which is I direction. So recall from here, I have here as my R. So we recall that R is equal to Xi plus what? Yj. So the magnitude or modulus of this vector, remember from what we did when we talk about some things that are important we should discuss in this objective here. We will write this as the square root. After all, is actually obtained from this right angle triangle we have here. In the sense that here is x and here is also what? Y. So what it means is that for us to find the magnitude of this, which is written as this, we say that this square is equal to x squared plus y squared. Meaning that r alone, that is the magnitude of r alone, is equal to the square root of what? X squared plus what? Y squared. This is actually where it was obtained. So, having done this, this particular expression here is what we call the magnitude or modulus of what? A given vector that is represented in a plane. In a plane, in the sense that it is represented in I and J direction alone. So, before we now talk about the three-dimensional vectors, so that is it. Now, this is the expression for magnitude of what? A vector that is represented in a plane. Then after this, we are quickly going to look at the direction cosine of a vector. Direction cosine of a vector. Now, direction cosine of a vector direction cosine of a vector. Still recalling back to that diagram we have initially, is our OR, P, and X, R, Y, just like we have before. We know that, please, I want you to listen attentively. We know that the resultant OR here makes, let's say, it makes an angle with the x-axis and also make an angle with the y-axis. So let's call the angle OR makes with the x-axis to be alpha, and call the angle it makes with the y-axis to be beta, just like this. So the direction cosine, there are two direction cosine here. The first direction cosine is cosine of angle alpha and cosine, and the second one is the cosine of angle what? Beta. So the cosine of angle alpha is the cosine direction or direction cosine of the vector, which is the vector OR, which is represented as small letter r, in the x direction. While the other one is the direction cosine, which is cos b or beta rather, is the direction cosine on the y direction. So let's take note of that. So the two direction cosine are cos alpha and cos beta. Now, what are the values of cos alpha and what are the values of cos beta? Because those are the direction cosine we are talking about. Now, for us to obtain that, we can obtain that from this triangle because these are two right-angled triangles, right? So for us to find that, we can find that by obtaining using the trigonometric ratio, because we know that trigonometric ratios are used in solving right-angle triangle problems. So, for us to find cosine of an angle, we require the adjacent side of that triangle and the hypotenuse side of that triangle, right? Okay. Now, for us to find the cosine of alpha from this triangle here, we are going to consider triangle ORN, right angle triangle ORN. So, Adjacent side of this triangle is what? X. While the hypotenuse side is the modulus of the what? Of the vector. Remember we said that when we obtain the modulus or magnitude of a vector, we say that this magnitude OR can be obtained as the square root of x squared, the square root of x squared plus y squared. So this direction cosine in x direction can be obtained or written as x over the square root of what? X squared plus y squared, because that's the hypotenuse of this right angle triangle. Also, direction cosine in the y direction, which is cos beta, is giving us y over modulus of r. So this is also the same as y over square root of x squared plus y squared. So these are the direction cosine of this vector OR in x and the y direction respectively. This is for x direction and this is for y direction. You can pause, take notes, so we can now go into solving problems. But before we solve problem, I'm also going to express the unit vector in terms of component vector, the terms of component vectors of a given vector. Alright, let us write this. So the unit vector in a given direction in terms of component vectors. Alright, we recall that the unit vector, let's say, in the direction of, let's say, a vector r is written as r cap. That's the unit vector. Now, and this r cap is such that r is equal to the product of r times what? Times r cap. I will now say that r cap is equal to r over magnitude of what? R. That's what we said before. Now, if we have a vector, let's say r, giving us x in direction of I plus y in the direction of j rather, then the unit vector in the direction of r will be written as this. So and that will be equal to x I plus yj all over the modulus of what? R, which is the same as x squared plus what? Yj. So, where, if we recall what we said that r cap is equal to r over modulus of r. That's what we say. So, where r cap, this is r and this is r, right? So, this is modulus of r and this is also modulus of r. So, this is how we can represent a unit vector in terms of its component vectors. Now we're going to solve an example so we can appreciate all of this we've been talking about. Alright. Okay, we're going to take the example. I want to pause. Alright, so we're going to end our session, the session of this class here. So this class will continue from the next video where we are going to solve practical examples and make it more details for a proper understanding. So make sure that you watch the next video that is following this one, which the link will also be posted maybe below or above the video. See you some other time. Bye.